when we look at Earth, we can see that there is a lot of rocks everywhere, and we can take very big amounts of a sample, more or less everywhere. And we know also that Earth is an inhabited planet. So theoretically, it should be very easy to establish when Earth became habitable and when life began to develop on it. And in fact, what we will see is that this is really a tricky problem. It's not so easy to determine when life appeared and how life appeared on Earth. So, looking at the very early Earth, there are two kinds of theories. One is a theory that says that at the beginning of the history of the Earth, that was a chaotic Earth with a magma ocean everywhere, meteorite falling down every minute, and so on and so on. So some kind of hell. This is the reason why the first area of the Earth history is called Hadean. And other people consider that, in fact, at the very beginning, the Earth was calm, cool, with ocean, continents. So, two opposite views. One is the hell, and another one is, well, Earth more or less like the Earth that we know today. So, what I would like to do is to find and to discuss some clues about the early history of the Earth, and as some kind of conclusion to not decide but to give arguments in favor of one or the other model. So we have seen this picture, or this kind of picture, many times this morning. This is the formation of the solar system in 5 or 6 steps, from the collapse of interstellar cloud and formation of planets, giant planets and telluric planets. But the question is, when this story started, what is T0 for this the history of our planet? So when we look at some very primitive meteorites, just like this one, some chondrite, we can see chondrules, just like here, and some inclusions in white here. The same, another meteorite where we can see the white inclusions here, and of course chondrule more or less everywhere. When we look at the composition of this kind of meteorite, we can see the colors can be translated in terms of chemical elements. We can see that most of the chondrule here are in red. They are magnesium rich. They are made of olivine and pyroxene mainly. While these inclusions are calcium and aluminium rich. And of course, you know, these are the calcium aluminium rich inclusions that we can see here. So they are inclusion. So that means that they form after the surrounding. So if we try to establish some kind of relative chronology, we can say that the first to crystallize was the calcium aluminium-rich inclusion, and after the chondrules. And if we look now at the temperature of crystallization, we can see that the CAI, calcium aluminium-rich inclusions, have a very high temperature of crystallization, while silicates have lower, and so on and so on. So certainly, in the history of the solar system, the first matter that crystallized were the calcium aluminium rich inclusions. Okay, the same in white. So now if we use some isotope dating method, here we use a lead-lead method. So we can see for the chondrule an isochrone whose age is 4.5647 billion years, while the CAI are slightly younger because they have an age of 4,5685 million years. So they are few million years older than the chondrules. So this corroborates what we have seen with relative chronology. So the age adopted as the T0 for the solar system, at least by geologists, is this age of 4.5685 billion years. So this asks a problem, because this age is obtained with a very good accuracy, very good precision, but from the analytical point of view. But in fact, this age is the age of condensation of the calcium aluminium rich inclusions. This is not the age of the beginning of the collapse of the cloud. And this is not the age of the formation of the telluric planets. So, okay, we have a very precise age that we consider as the age for the beginning of the solar system, but of course we give a very precise age for a process that lasted a long or more or less long period of time. So we need to remember that this is not the age of the very beginning, and not the age of the beginning of the Earth itself. But this is a reference. We'll look at some words that I will use. This is a geological time scale. So the beginning of the history is the age obtained on CAI, inclusion in meteorites. So this is the age of the Earth, considered as the age of the Earth's accretion. We have an age of 4.0 that corresponds to the oldest rocks that we know on Earth. And before, this period is called Hadean. After, we have another important period, 2.5 gigayears. The period is called Archean. And this limit here between Archean and another period called Proterozoic is the period when the Earth began to work as a modern Earth, with the same kind of plate tectonics and so on. While before that was different. And I will talk about this in the second part of the afternoon. So the other limit, 0.5, is an explosion, what is called the explosion of life at the Cambrian. And of course, this one is today. So first, I will give you some, and show you some picture of these rocks are 4.0. These rocks are found in Canada, in Acasta, here in the northwest province. And they correspond to small outcrops. You can find them here, so just in this place. So, okay, the rocks and the place with a nice beach and organized to welcome geologists. And here is a photo of these rocks. You can see gray gneisses here, cut by pegmatite, and the age of the pegmatite is 3.6. But what is interesting in these rocks, the gray rocks contain minerals called zircons. So here are these rocks with a strong foliation. They are gray. And they contain crystals of zircon whose age is 4.03, 4.04. So this is the oldest age obtained in a rock today. Maybe in the future we'll see more, but found other older rocks, but this is the oldest we know. But in fact, there is something interesting. If we look at some of the crystals from this area, so these ones are not 4.0, but 3.9 millions. So we can see here a crystal, but we see also here a core with a dark gray color here, and the ages obtained on this core are 4.2 billions. So 200 million years older than the Acasta gneisses. So these minerals, zircons, are very resistant to weathering, to alteration, and in fact, the Acasta gneisses were formed by melting of sediments. And in these sediments, there were very old zircons, just like here, rounded, and they have been incorporated in the new magma at 4.0. But the point important is that these zircons formed in granite. So that means that before Akastagnasis, there were granite 200 million years before. So we do not know these rocks, they disappeared, they were eroded and so on, only survive zircon crystals, but they are a proof that during the Hadean we had continental crust. We do not know it, but we have proof that it exists. So I will develop this a little bit later. So one of the big problems on Earth is that we have plate tectonics and that we have erosion, alteration, so rocks are destroyed, return, via subduction, they return to the mantle and so on. So the very old rocks were not preserved, and we are obliged to try to find information on other planets, and for instance, on the moon. If you look at the moon, for geologists, this is very simple. There are white and black parts. So the geology is very simple. And the moon has a big advantage, is that geologists can go and take samples on the moon with, as you can see, very sophisticated tools. And if we look at the moon, the white parts here consist in white rocks that are made up of plagioclase. We can see here in thin section a lot of plagioclase. And the rarest composition of these rocks is with very low content in rare earths and a positive anomaly in europium. Now if we look at the black rocks, they are basalts, submarine basalts. So here a thin section of this basalt. And the rare earth pattern is exactly the opposite. This is high rare earth content and a negative anomaly in europium. So when these rocks were discovered and analyzed, people say, okay, they are coming from the differentiation of a single parental rock that had this kind of composition. And the idea was that at the beginning of the history of the moon, there were rocks or magma with this composition, a flat pattern, and that was divided in two parts, one impoverished in rare earths and the other one enriched in rare earths. The idea was that I come back, this magma, in fact, occupied a very big proportion of the moon, and that it formed what is called a magma ocean. So, in this, we do not know exactly the proportion of the moon that was molten, but a very big thickness of the moon was molten, and this is what we call magma ocean. In this magma ocean, some minerals crystallize, for instance, the plagioclase, the feldspar that we have seen. And if we look here at the density of minerals, and here the density of the magma, we can see that on the moon, the density of feldspar is lower than the density of the magma. So it will float and move toward the surface. And just the accumulation of this feldspar will make a crust made of feldspar, called by geologists allotocetic crust. On the opposite, the other minerals, olivine and pyroxene, have density greater than the magma, so they will sink. So in this magma ocean on the moon, some minerals floated, giving rise to the anorthositic crust, while the others sink at the bottom of the magma ocean. But there was what geologists call a differentiation process. We started from homogeneous magma, and we divided this homogeneous magma in a crust and what we call a mantle. So the crust is made of feldspar and the mantle of pyroxene and olivine. Okay. So we started with this composition, and accumulation of feldspar gave anorthosite, and the rest of the mantle gave what is the source of the basalt of the moon, of the marine basalt. So this is some kind of differentiation. So this process was a very important process because we can see anorthosite in more than one half of the moon. That means that the process affected the whole planet. And the genesis of this anorthosite was not a process taking place in a small part of the moon, but at a planetary scale, was a planetary scale process. Okay, now when we try to obtain the age of this anorthosite, so here we use another system that is samarium neodymium isotopes, and they give an age of 4.456 million years. That means that the process of formation of anorthosite and of differentiation into the magma ocean took place very early in the history of the planet. There was a very early process in the history of the planet. And in addition, if we can date minerals like this, the minerals need to exist. So this is the age of their crystallization. And the crystallization of the ocean magma is the end of the history of the ocean magma. So what we can say as a conclusion is that the magma ocean formed very early in the history of the planet, and the scale of the process was planetary. It affected the whole moon. Now, what about the Earth? So, if we make some very rapid calculation, for instance, the gravitational energy released by accretion, if we assume, that is of course very far from reality, that everything was released instantaneously, we have 1,500 Kelvin for the moon and more than 30,000 for the Earth. Gravitational acceleration was more important, of course, on Earth than on the moon. And this is very important because plagioclase that give rise to anorthositic crust form at low pressure near the surface. But as the gravitational acceleration is lower on the moon than on Earth, we can have plagioclase on the moon up to depth of 165 kilometers. On Earth, due to the higher gravitational acceleration, only on 27 kilometers or 30 kilometers. So that means that the thickness of the magma ocean on the moon and on Earth, if it existed, doesn't allow the production of very big amounts of plagioclase, of feldspar on the Earth. In addition, water availability was very important for the behavior of plagioclase. For instance, if here I put the amount of water in the magma ocean, and here the density, we can see that for basalt, the density of basalt decreases with the amount of water. Here, these are basalt at different pressure, here near the surface, and here at 6 or 7 kilometer depth. So the density of basalt decreases with the amount of water. And if now I put here the density of plagioclase, we can see that in a dry system where there is no water or almost no water, which is the case of the moon, the density of the plagioclase is lower than the density of the magma. So, as I said, it will float and go toward the surface. Why on the Earth there is water available on Earth? So, the density of the plagioclase is greater than the density of the basalt. So it will sink. So we cannot expect an anorthositic crust on the Earth due to this and all the other arguments that I have presented before. Geochemistry don't show any evidence of anorthositic crust on Earth. But what about magma ocean on Earth? If we look at rocks called komatiite, these rocks are very special because they correspond to very high degrees of mantle melting, and I will tell you more later. We find on Earth 3 groups of komatiites. So here they are plotted in a diagram with gadolinium, ytterbium, and here aluminium, titanium. And we have 3 groups. One depleted in heavy rare earths, one with chondritic value. The chondritic value are this line, vertical and horizontal. So the chondritic value is here, with flat patterns. And of course the third one, enriched in heavy rare earths. But what we can see here, which is an important point, is that the enriched and impoverished pattern correspond to rocks older than 3.4 billion years. We have not young comatiite with this kind of pattern. The young comatiite all have flat pattern like this. So this is a very important point. That means that this kind of feature are observed only in the younger, or for us the oldest rocks formed early in the history of the planet. Here, just like what we had on the moon, we can see the complementarity. If you have a flat pattern here, we can say that this is a differentiation of enriched pattern and impoverished pattern. So we can conclude that this one is not differentiated. This one and this one are differentiated. If now we look at the minerals that can give such a result, here we have what we call partition coefficient for gadolinium and ytterbium in different minerals. And there is only one that is able to fractionate strongly this pattern. This is garnet. Garnet is the only mineral that can fractionate this pattern because it can accumulate, contrary to other minerals, it can accumulate very huge amounts of heavy rare earths, and so it will be very rich in heavy rare earths and poorer in middle rare earths, just like gadolinium. So there is only one mineral that is able to produce this fractionation. This is garnet. So we can complete this, give more information. Indifferentiated is what we call chondritic. The one with enriched in heavy rare earths correspond to garnet accumulation, and the one impoverished in rare earths correspond to garnet removing. So it seems that we have these three kinds of patterns. And this is interpreted in terms of magma ocean. I will explain why later. Here is another diagram based on short life radioactivity, samarium neodymium in the samarium neodymium system. The half-life is very short, 100 million years. But in this system, all the rocks from the Earth, or most of the rocks from the Earth, fall in the same range with value of this parameter between -8 to +8. All the rocks fall in this range, except rocks from Isua in Greenland, from Nunavut in Quebec, and from Akasta. And what is the particularity of all these rocks? All these rocks are older than 3.8 billion years. So they are among the oldest rocks on the Earth. So this is what we see, great homogeneity for all the rocks on Earth, except for the very old ones. Some are enriched, some are impoverished, but there was some differentiation in the early Earth at that time. Okay. So on Earth we have seen we have no chance, if we had a magma ocean, we have no chance to have anorthosite. So what we could have is a cumulate of olivine, pyroxene, and garnet. And, okay, so if we look at the rocks that were not affected by crystallization, we have chondritic and flat pattern. Now, as garnet has a high density, it sinks in the magma ocean. So, at the bottom of the magma ocean, we will have accumulation of garnet, so we will have this kind of pattern. And at the top of the magma ocean, as garnet sinks and now is at the bottom, it will be impoverished in garnet, and we will have this kind of patterns. So that means that in the Earth magma ocean, we do not have the same patterns as on the moon, but we have not enrichment or impoverishment in plagioclase, but in garnet. The bottom of the magma ocean is enriched in garnet, and the top is impoverished in garnet. So this is a situation that we can observe before 3.4 billion years. Now we have seen this, but we can write this equation also like this. That means that the differentiation of a chondritic mantle can give these two kinds of patterns. But now if we mix these two kinds of patterns, we can obtain something flat just like here. And this is one of the hypotheses that we have. That means that in this magma ocean, convection was active and rapidly, well, rapidly is 1 gigayear. So, okay. Not so slowly. It can rehomogenize the magma ocean such that the composition of the whole magma ocean would become something like that. So that means that, what is the next one? Not. That means that before 3.4, the magma ocean, the Earth mantle was heterogeneous, differentiated. That means that we have the three kinds of rare earth pattern. And that after 3.4, convection rehomogenized to everything, and we have flat chondritic patterns. So that means that the process of differentiation took place in the very early Earth, such that we can have this differentiation very early in the history of the Earth. So, just a beautiful picture. And maybe, at the very beginning, the Earth, our planet, looked like something like that, with a magma ocean covering most of the planet. You know that the people, the specialists of magma ocean, think that the thickness of the magma ocean, or the depth, was about 1,000 kilometers. So these are what we can say about magma ocean. Now, another problem is that, as it was said this morning, that the Earth's result of collision of planetesimals and so on. And when we look at, for instance, today meteorite, we can see iron, for instance, in this chondrite, iron in white, and in gray, these are silicates. And what we can see is that in chondrite, iron and silicate are more or less homogeneously distributed in this meteorite. Now, you learned when you were very small at school that Earth is made up of an inner core, solid, and outer core that is liquid, and they consist in iron with more or less nickel, and that the outer parts are mantle and crust, and that they correspond mainly to silicates. So if we look at the Earth today, of course what we see is that today metal and silicate are separated. So they are supposed to be formed by collision of meteorite where metal and silicate were homogeneously distributed. And now we have a planet with separation of metal and silicates. So the question is, when did the separation take place? When this event took place in the history of the planet? There is isotopic system that is very interesting. This is the decay of hafnium-182 into tungsten-182. And the half-life is very short, is 9 million years. So, what this means is that after less than 60 million years, all the hafnium of this isotope of hafnium have disappeared. So this system can be used to date processes that took place before 60 million years on the Earth. In addition, hafnium is what we call lithophile element that likes silicates. While tungsten is a metal, it is called siderophile element, and it will be incorporated into metal, into iron. So we have here an isotopic system that can allow us to date very early processes, but also the behavior of the parent and son and or daughter elements will be shared between silicates, that means mantle, and metal, that means core. So let us assume that the core mantle differentiation took place more than 60 million years after the formation of hafnium. So the whole hafnium would have decayed into 182 tungsten, and all the 182 tungsten will be in the core, nothing in the mantle. Now, if we assume that this process took place very early, less than 60 million years after the nucleosynthesis of hafnium, of course, one part of hafnium, 182, have already decayed into 182 tungsten here, but some part remain of hafnium, not the whole hafnium decayed into tungsten. So one part of this remain as hafnium and have been incorporated into the mantle, into the silicate. And this is only after having been trapped into the silicate that it decays into tungsten. So the idea is very simple. If we find 182 tungsten in the silicate, in the mantle, the significance is that the differentiation between silicate and iron took place before 60 million years. So this is the conclusion. Maybe it's more easy to say this in one sentence. So, of course, if I speak about this, you can imagine that we find some 182 tungsten into the silicate. And this means that core mantle differentiation took place very early in the Earth's history, less than 60 million years after the nucleosynthesis of hafnium. Okay, now if you like geochemistry, we can play with another system, is 182 and 183 tungsten, here plotted against time. So we know the curve of evolution of a chondritic mantle. So theoretically, if we would not add separation of metal and silicate, we should have this value for the mantle. And in fact, we have this value. So if we make the calculation back, we can determine the period of separation here, and we find that the separation, of course this is less than 60 million years, but the separation is about 30 million years. So something very early in the history of the Earth. So, okay, a very early process was this differentiation. However, this method of dating has limitation. What I presented is the ideal case where 182 tungsten hafnium is transformed into tungsten. In fact, on the Moon, we have seen that some isotope of tantalum, if reacting with a neutron, is able to give 182 tungsten. So this means that 182 tungsten is not always coming from decay of 182 hafnium, but can be also cosmogenic. And we do not take this into account in the calculation of the age. Another point is that we assume that one ratio of hafnium isotope, 182, 180, is constant in the whole system, in the whole solar system. We assume, but we have no proof that it is constant in the whole solar system. If it is not constant, this will change the value of 30 million years that we obtain. So, my comment on this is that the age of 30 billion years, there is a lot of uncertainty around this age. But certainly, the differentiation of mantle and core took place before 60 billion years. This is almost sure, even if we have this kind of uncertainty on the origin of isotopes. Certainly it took place extremely early. Maybe not 30 million years, but very early in the history of the planet. Okay, so this is very important for life. Because you know that in the liquid core today, there is a convection, and this convection gives rise to the magnetic field. So, this is important because the differentiation of the core is something necessary for the development of magnetic field on Earth. And you know that magnetic field protects our planet against the solar wind. So this is a good protection of the surface of our planet. So this has implication for life apparition and development. Okay, I like this picture, so it is here. But what I would like to say is that it is necessary to have a differentiated core in order to develop a magnetic field. But this doesn't mean that magnetic field appear immediately after the apparition of the core. So one of the questions that we can ask is, when did the magnetic field begin to work? So here is a diagram. This is done in 2 years ago. We have here the strength of the magnetic field. So we can see in here time, and we can see that it changed quite a lot during time. Some recent data continue this up to 4.2 billion years. And okay, what we can say is that it existed a magnetic field at 4.2. But as we have no rocks or no magnetic material before, we cannot say that it appeared immediately after the formation of the core itself. But very early there was a magnetic field. Another evidence was published 2 or 3 years ago. It is based on the nitrogen isotopes, so the ratio between 15 and 14 isotope of nitrogen, plot here against the isotope and the element ratio. Crust and sediments plot here, so they have a positive value between, let us say, 5 and 15. And the people who have done this study, they study hydrothermal quartz, and in this quartz there were some small pockets of fluids, of water. So they study this water, and they see that all the data plot here. So they correspond to what we could say a mixing between crust and sediment and water. Or saturated water saturated with air. So that means that at 3.5, the composition of this water was the same as today. So that means that it has not changed since a very early Archean. And this is important because if we consider the values for the solar wind, we should expect lower value, because the value, this ratio, for the solar wind is minus 240. So that means that if Earth was not protected against the solar wind at that period, we should expect very low delta 15 nitrogen. This is not the case, so that means that there was already a protection against the solar wind. So the conclusion is that we cannot fix precisely the date when magnetic field appeared, but that it appeared very early in the history of the planet. And this is, of course, very important for life. For instance, if we look here, we have time, 2.5, and here is the beginning of the Earth. Here we have a ratio of isotopes of neodymium. And if the mantle was not affected by extraction of continental crust, we should have something plotting along the red line. Not above, not below, just on the line. And what we can see here, in the oldest rock that we know, for instance in Akasta, we have values of +3 and maybe +4. That means that the mantle at 4 billion years was already affected by the extraction of continental crust. That means that continental crust has been extracted from the mantle before 4 billion years. So that means that continental crust existed before. We do not know it because it has been eroded or recycled into the mantle by subduction or something like that. But we have indirect evidence of this. Since 20 years, we know not the rocks, but only minerals from a place in Australia that is called Jack Hills. So here is a picture of Jack Hills. And in this place we can find sediments. So here is a big conglomerate with the big boulders in the conglomerate, and some sandstones here. And in this conglomerate and sandstone, they found, the geologists working there, found crystals of zircon. So zircon is some kind of magic mineral because it contains uranium and thorium, so very easy to date. And in addition, it is extremely resistant to alteration. So this can be considered some memory of the Earth. So they found this kind of zircon crystals. And some of these zircon crystals give very old ages, 4.35 in average. I must be very clear, the zircons belong to a rock, but this rock has been totally destroyed. But only the zircon crystal resisted. So these minerals are the oldest material on Earth, but the acastagnices are the oldest rocks, a rock being an assemblage of minerals. The rock here has disappeared, only survived zircon crystals. So the age is this age, and even a very old age has been found here, 4.4 billion years. But this age is discussed by specialists, by geochronologists, because, as you can see, it has been obtained near a crack, a small fault in the mineral, small crack, and some people suspect that it could have been slightly modified by circulation of fluid in this crack. But this is not the case here. So the conclusion is that on Earth we can find not Hadean rocks, but Hadean material, just like these minerals. So the sediments in Jack Hills are 3.7 or something like that gigayears old, and they contain zircon of all the periods between 3.8 up to 4.4. That means that the zircons that we find, for instance here, is not an accident, something that an event that took place one time and never after. In fact, the production of zircon was at the beginning slow, but almost developed and almost constant during the whole Hadean. So that means that the process of genesis of these zircons was not an occasional process, but that it developed over a long period of time. So another thing interesting is that when a mineral is crystallizing in a magma, it can include other minerals that crystallize together with it in the same magma. So here I put a picture that I like very much, which has nothing to see with the Jack Hills, but this is a garnet in inclusion in a diamond. So during the growth of the diamond, it catches the garnet mineral crystallizing together with it. So it's possible to find inclusion of minerals in other minerals. And when we look at, here this is a microscopic picture of zircons from Jack Hills, we can find a lot of minerals, for instance in red, this is quartz inclusion, in green, plagioclase, and so on and so on. So there is a lot of mineral included into Jack Hill zircon, and the are minerals that were crystallizing together with zircon. If we look at these minerals, we can see that there is quartz, plagioclase feldspar, autoclase feldspar, biotite, muscovite that are mica, and other minerals. And you remember that quartz, feldspar, and mica are the main minerals in a granite. So that means that the minerals that were crystallizing in the same time as zircon were the minerals that we can find in a granite. In a basalt we should have found olivine, pyroxene, and so on. So these minerals are minerals from a granite. That means that the zircon crystallized in a granite, and you know that granite is a composition of the continental crust. So these zircons are now considered as a proof that the continental crust existed as early as 4.4 or 4.35 million years ago. That means that the continental crust appeared very early in the Earth's history. Less than 300 million years after the beginning of accretion, the continental crust existed on Earth. So this is a very important point. Everything seems to have been very rapid at the beginning of the history of our planet. I told you that zircon can include small amounts of uranium and thorium, but it can also include very small amounts of titanium. And something interesting is that the amount of titanium that a zircon crystal can accept depends on the temperature. And here you have the logarithm of titanium content in zircon crystal, and here you have the temperature. And you see that higher the temperature, higher the titanium content. That means also that if you can analyze the amount of titanium in a zircon crystal, you can determine its temperature of crystallization. So, of course, this has been done for the zircon from Jack Hills, and all the geologists were very much surprised by the results because the temperature is very low, around 700 degrees Celsius. So we should expect on a very early Earth very high temperature, 1000, 1400, something like that. No, the temperature is very low. So that was a very surprising result. Now, this is important because if we look here, we have temperature, here the pressure or depth, and here the solidus of a dry granite. That means that on the right we have a liquid, a magma, on the left we have a solid rock. Now, if we have water in the system, this totally changes because this solidus moves here. So this decreases the temperature of melting. Here we will have magma and here solid. So if we consider one depth here, if we have no water, melting will take place at more or less 1000 degree. If we have water, at 650. So the presence of water decreases the temperature of melting. Now, if on this diagram we plot the range of temperature we obtained for Jack Hill zircon, we found this. This is the range. So we see that it is impossible to generate the parental magma for zircon by dry melting of something. We need to have hydrous melting. That means that water was necessarily available at this time. It was water in the system at that time in order to allow hydrous melting of the source of this of the magma that by crystallization gave zircons. Okay. So this is something important because this demonstrates that water was available at the time. Of course, the conclusion is not based only on this. And other people, more than 10 years ago, 12 years ago, studied a stable isotope of oxygen in this material. And today, mantle zircon value is 5.3 for mil. If now we plot in the same diagram the delta oxygen, 18 oxygen for Jack Hill zircon, we see that we have value greater than 5 or greater than 6, up to 7.5. So there is only one possibility, only one explanation for that, is that the source of the rock that gave the magma were affected by hydrothermal alteration at low temperature. Hydrothermals mean also water. Water was present in the source of the magma that gives the zircons from Jack Hills. So this is another argument in favor of that. Are you convinced? Do you like isotopes? I propose another system. The lithium isotopes. Here. So here are the mantle values with a sub-error range. And here is a pattern, is a histogram of values obtained on zircons from Jack Hills. So you can see that there is a wide range of composition here, from +10 up to -20 or something like that. Now, if we look at other, other rocks, Archean rocks, for instance, with name CTG, or well, Archean rocks, they plot in a more restricted range. If now we look at the composition of the continental crust in general, including Archean, but also more recent rocks, they also plot in a very restricted range. And now, if we plot here the composition of the continental crust affected by alteration, by weathering, so that means by the effect of water on the rock, we can see a very wide range of composition. So the people who have done this study 5 years ago, Bouvier and collaborators, they conclude that this pattern that we see of a distribution of lithium isotopes that we see in Jekyll zircons means that water play a role in their genesis. So there are a convergence of arguments in favor of the presence of water on Earth as early as 4.35 million years. That means that if we try to conclude, at the time, during the Hadean, we had continents and we had water. And I do not say that life developed at the time, but the conditions were favorable for the development of life, or at least of prebiotic chemistry. We had water, continents, magnetic field protecting the Earth. So this is a possibility. A last point, but we spoke a lot about it this morning, so I will go briefly. So if we look at the moon, or Mercury, or even other satellites of giant planets, we can see that there is a lot of impact crater at the surface of these bodies. So on Earth we do not find this impact crater because of plate tectonic, erosion, and so on. But on the planets without plate tectonics, we can find a lot of craters. And on the moon it was possible to date most of these craters. So we can see here the age of some of these craters. And we have a very nice curve here. And the problem is, are we allowed to extrapolate this curve or not? So if we extrapolate, of course, that means that before, let us say 4 billion years, that means that there was the flux of a meteorite arriving on Earth was extremely high, and probably the Earth looked like this. But there is a problem. If we consider the size of the crater, we can have an idea of the volume and the mass of the impactor. And if we go in this direction, back towards the origin of the Earth, we could conclude that the moon formed at 4.1 billion years, which is absolutely incorrect. So that means that we are not allowed to extrapolate like this. And of course, you know, the other alternative was that, of course, during the period of accretion, there was a lot of meteoritic impact. After, there was a cool, what is called the cool early Earth, and there was a catastrophic event that is called the late heavy bombardment. And in this condition, we had a period of 200 million years at the beginning where the Earth could have been something like that. Okay, I will not comment because this has been explained this morning. And in fact, the idea is that there was a migration of the planet Jupiter moving towards the center and Saturn going a little bit back. And of course, when they enter into resonance, there was this disturbed totally the system, such that the outer planet enters into the planetesimal disk here and ejected planetesimals of course, outside, but also toward the center of the solar system. This is called the late heavy bombardment. So, okay. So I consider that in this diagram, I consider that the big attack took place on Earth, and what is supposed to arrive at that time is, of course, when Jupiter and Saturn enters in resonance to one. They ejected Uranus and Neptune toward the outer part of the system. So this is an explanation for this accident that is supposed to arrive not only on Earth but on other planets. And maybe the Earth resembles something like that, with a lot of crater at 4 billion years, with a lot of crater but occupied by water because the water was available at the time. Okay, I will finish on time. Just one slide that I like. If we consider the history, during the early Hadean, before 4.4, because we know that the magma ocean was crystallized at 4.4, of course, there was a magma ocean. There was no liquid water, maybe magnetic field, maybe not. So, for me, at least, it's difficult to imagine the development of life during this period. Even the prebiotic chemistry in a magma ocean, for me, is not easy to imagine. So I think that the very, very beginning of the Earth's history was not favorable for the apparition of life. Between 4.4 and 4.0 billion years, as we have seen, we had continent, we had water, there was a magnetic field. So I do not say that life appeared and even that prebiotic chemistry developed at the time, but the conditions were favorable for that, for the development of prebiotic chemistry and even for life. And what we will see later, in the second part, during the Archean, we had continent, plate tectonics, and so on, and we have also traces of life. So life, the condition was not only favorable for the apparition of life, but for the development of life. And there is only one interrogation, is what is the role played by the heavy bombardment? So as I remember what has been said by the speakers this morning, maybe the late heavy bombardment doesn't exist. Okay, so no problem. But if it existed, what was its role? Was it sterilizing the Earth or not? Was it strong, extremely strong, such that, for instance, most of the ocean evaporate and life disappear? So there is a lot of question about this late heavy bombardment. And this also is important. Imagine that life developed during this period was destroyed by the late heavy bombardment. That means that it appeared after. So that means that life should be something very common. Okay, I will finish with this philosophic sentence. Okay.